Hello and welcome. Today we're going to be talking a little bit about the scientific method. What we're going to do is list the steps in the scientific method, and I'd like you to be able to identify or be able to write any of the following: a hypothesis, an experiment, a variable, independent variable, dependent variable, what a scientific law is, scientific theory, a constant, and a control in an experiment, what those would be. So, by the way, you're not going to find that I ask you to flashcard type information where I give you scientific method and then you write an organized way to find an answer, solve a problem, or investigate something. I'm not going to ask you to memorize these definitions, but to be able to use them to answer questions. So, scientific method. A hypothesis is a testable prediction, not just a guess. It's based on something that you already know, and you might include research you have done. It's very often an if-then statement. An experiment is just an organized or logical method of testing a hypothesis. Variable is something that changes in an experiment. There's two types, independent and dependent, that we're going to look at. An independent variable, this is the factor in an experiment that is changed directly by the experimenter. It is the cause of change. It's what you change directly. The independent variable is what changes as a result of changing the independent variable. It is the effect. It is the effect of the change, or it is the change. A control in an experiment is used for comparison. It is typically the part of the experiment or the experimental group with the normal conditions, the normal independent variable, or either gets no treatment. It does not get the independent variable. And that's usually the trickiest one for kids to pick out, is the control in an experiment. Constants are pretty easy. They're one of many different factors that aren't supposed to change in an experiment. So things that we want to keep the same, that is a constant. And they're constant, they don't change. And the conclusion is basically your results, whether or not you accept or reject your hypothesis, and why. So everything in the universe follows natural laws, and as scientists, we seek to understand these natural laws. In the real world, these laws can't be broken, unlike in the Matrix, where he can stop a hail of bullets pulling at him just because he can control the program. In the real world, we can't do that. Science can figure out these natural laws or patterns because they don't change. But sometimes our ideas about them do. Sometimes we have false ideas about them, and then they later get corrected and then often corrected again. So for example, the law of gravity, we can figure out gravity because it keeps acting the same way. It doesn't change. When we drop something, it falls down. Although our understanding of gravity has changed significantly from simply knowing that it causes things to fall down. Einstein told us that gravity is a result of warped space and time due to mass. So scientists seeks to answer questions, and there are questions that science can answer and questions that are not scientific questions. For example, a good type of scientific question is, why do my armpits stink when I'm hot or nervous? Well, that's because when you're hot or nervous, your armpits sweat, and the stink is caused by bacterial growth, and bacteria like it when it's a warm, wet environment. So when you perspire, you're giving it a good environment. The bacteria grow, and then they stink. A bad scientific question, or a non-scientific question, would be, why is pop music better than classical music? Science can't answer that question because that is a matter of opinion, right? Okay, so how to go about finding these answers? Rather than just bumping into walls, we want to follow a system. And the system that scientists use to answer questions is the scientific method. Okay, and 6 common steps to follow in the scientific method. You'll sometimes see 7 or 8. It's really the same scientific method. It's just sometimes they collapse, they expand. What I've considered as, for example, test the hypothesis. They might say write a procedure, and then follow the procedure. Break it up into more steps. But anyway, so step 1, state the problem. Step 2, gather information. Step 3, form a hypothesis. Step 4, test the hypothesis with an experiment. 5, analyze data. And 6, form a conclusion. Now, this is normally where I would pull a flashlight out of my desk, okay, and I would tell you that I'm going to show you something with this flashlight, and I try to turn the flashlight on, and I show you guys, and I flip the switch back and forth, and there's no change. The flashlight doesn't turn on, and I'll say, well, darn it, why did these things always happen to me? I try to show you something with the flashlight, and my flashlight doesn't even work. And then someone will usually say, well, change the batteries. And I'll say, oh, that's a good idea. And I'll go ahead and pull a fresh set of batteries out of my desk and I'll replace the batteries and then I'll turn the flashlight on and it'll suddenly work. That's my flashlight demonstration. And I do that because that's a very, very fast way, very quick, concrete way of doing the scientific method. We stated the problem. What was the problem? My flashlight doesn't work. Okay. Gather information. Well, I did that by asking you guys. So you guys are flashlight experts. So I asked you guys, although I could have done internet research or gone to the library or something along those lines. Okay, so I did do research. I don't know why it went away. We formed a hypothesis, and my hypothesis was if I replace the batteries, then the flashlight will work. We tested the hypothesis with an experiment. We changed the batteries and tried it again, and the flashlight, lo and behold, worked. Now, analyze the data. I don't think we did a whole lot of data analysis other than just looking at the light and saying that it did turn on. And then we did form a conclusion. The hypothesis was true. The flashlights work after I've replaced the batteries. So that's the conclusion we came to. Now, I can't totally come to the conclusion. I have not proven, by the way, that my batteries were dead because any number of things could have happened in the experiment because I couldn't control every variable. For example, I could have rattled a loose connection loose or knocked it into place when I was changing the battery, and maybe there was just a loose connection that had to be shaken up. Or in the case as what I did, the batteries were actually good. It just had a piece of tape over it so that we couldn't make an electrical connection. But we really can't conclude conclusively that the batteries were dead from that experiment. We could do more experiments and we could strengthen that hypothesis. Now, you don't have to follow these steps exactly to be using the scientific method. A lot of times you might be skipping the gather information part if you already know enough. Sorry, dog got a little mouthy there. If you know enough information, you don't have to go research anything. But what if I had replaced the batteries and the flashlight didn't work? Well, what you would do is tell me something else you might think that might make the flashlight work, knocking it on the desk a couple times or maybe replacing the light bulb. But what I would do is form a new hypothesis, and then I'd test that hypothesis and form a conclusion there. So an example of me following the scientific method was this is some years ago, but my TV didn't work. And so I do not know that much about TVs. So what I did a lot of internet research, and I found people that had the same model and had similar problems and what they did to fix it. So a lot of these people said if you replace these couple chips on the circuit board, this is a big old circuit board. It's yeah, like three feet long. Anyway, they said if you replace these chips, then your TV will work. So that was my hypothesis. I ordered the chips. They came from China. Took a while to get there, and I replaced the chips and retried. And again, I didn't really analyze the data in this case, but per se, at least nothing very, at least nothing too formal. I did analyze the TV did turn on, and then I came to the conclusion that the hypothesis was true. The TV worked after I replaced the processor chips. So let's go through with another experiment, one that's maybe a little bit more scientific. You might argue against that. So step one, state the problem. Well, I want to know if I put aspirin in the water that I spray on corn plants, if it'll affect how quickly the plants grow. So that might be my question. I think I'm going to increase the food supply by spraying aspirin water. Step two, gather information. You might research whether aspirin and corn have been tested before. You might research to see if corn gets headaches or if it can feel pain. Step three, form a hypothesis. So this is our if-then statement. So we think probably that if we spray the corn plants with aspirin water, then they will grow faster. So we think including the aspirin in the water is going to make the plants grow faster. So step 4, oh, the independent and dependent variable. Let's see if you guys remember this from middle school. The independent variable is what I'm changing directly, and the dependent variable is what changes as a result. The independent variable is the cause, the dependent variable is the result. So what should be the cause of the change? Well, the cause of the change should be the aspirin. If aspirin, okay, then the dependent variable would be faster growth, we think, the rate of growth of the corn plants. So that would be that. So you would come up with a procedure. Now, normally you do more than one trial or more than one corn plant in this case. I would want to use more than one corn plant. Let's say I had, or I'd want to do multiple corn plants. If one of my corn plants died, I might conclude that the aspirin killed it and maybe it was just a sickly corn plant. So, all right. Constant. Constants are things that we want to hold the same between everything in our experiment. So the constant that we would want to keep the same with our corn plant would be the type of soil. We'd want to keep the same amount of sunlight. We'd want to keep the same amount of water. The only thing we'd want to change is the aspirin. We'd want to keep the same humidity. Any other, basically everything other than the aspirin, we'd want to keep the same. What would the control be? This is the tricky one for kids. The control is the part of the experiment that gets the normal treatment or the no treatment. Since we're treating the plant with the aspirin, the plant that does not get the aspirin, okay, does not get the independent variable, no IV, no aspirin, that is going to be our control group, and that's the one that we're going to be comparing to. So, all right. So we do our experiment and we get our results. So this is the amount of aspirin down here, and this would be the height of the corn plant. And so this is my data for that. And what conclusion do I want to come up with? And I did a bad thing here by not labeling my axes. That's not good. Sorry about that. What would I conclude from this? Well, it doesn't really look like the aspirin had any effect, and if it did, maybe a slightly negative effect on the growth of the plants. But certainly it did not make them grow any faster. Although you might almost say that no, really. You would say it's either no result or slightly negative result. Okay, so